Hi, everyone. Welcome to another LIC class. In the previous class, we spoke about first order high pass filters. And specifically, we started a little bit speaking about active high pass filters. So an active high pass filter is a combination of an active element, in this case, an op amp, which is the amplifying part, and a passive high pass filter. The difference between a passive high pass filter and a passive low pass filter is the location of this capacitor. For a low pass filter, the capacitor was in parallel. For a high pass filter, it's in series with the input of the op amp. We learned in reality, we don't have such a thing as an active high pass filter because an op amp itself has an upper cutoff frequency limit, which limits the upper cutoff frequency of the op amp. So technically, an active high pass filter is a band pass filter with a very high upper cutoff frequency. How do we determine the upper cutoff frequency? The upper cutoff frequency for an op amp was the gain bandwidth product over A noise. And we also solved a couple of problems with different op amps and different A noise. And we also learned from previous chapters that if you want a bigger or larger frequency response, you need to lower your gain. So there's a trade-off between the gain and the frequency response. The higher the gain is, you're going to have a smaller frequency response. And the lower the gain is, you're going to have a larger frequency response. So there's a trade-off there. So what should we do if we want to design a high pass filter? First, we have to pick an op amp that has a pretty high upper cutoff frequency. So if you want to design a high pass filter that filters everything above 50 hertz, if the upper cutoff frequency of that op amp is 1 megahertz, for example, the frequency would never reach 1 megahertz. So you're going to be in the safe zone. So in theory, this would act like a high pass filter. Again, when you are designing an active high pass filter, the upper cutoff frequency of the op amp should be so high that the input frequency never reaches that point. Okay. If I design a system, for example, let's imagine the opposite. Imagine that I want to design a high pass filter, and the cutoff frequency of that high pass filter is around, let's say, 200 kilohertz. But the upper cutoff frequency of our op amp is, and I'm going to draw it with this, is around 300 kilohertz or 250 kilohertz. This is not going to be a very good high pass filter. We have to find an op amp that its upper cutoff frequency is around, let's say, 2 or 3 megahertz or 20 megahertz. So we would have space for the frequency response. So when designing an active high pass filter, you have to take in consideration the upper cutoff frequency of that op amp. In some systems, like if you want to filter out of 50 hertz, 60 hertz, an op amp that has an upper cutoff frequency of 1 megahertz is going to be more than enough. But in other applications that your lower cutoff frequency is around 200 kilohertz, 300 kilohertz, 1 megahertz, then a normal 741 would not even work because the upper cutoff frequency of that 741 is 1 megahertz. So you have to switch to a higher frequency op amp. So this is what these two slides are explain about. When designing an op-amp, again, it's better always to pick an op-amp that has a gain bandwidth product which is pretty large or pretty high. So an active high-pass filter or a single pole active high-pass filter is usually combined of a non-inverting amplifier and a passive filter. This is an example of us connecting a non-inverting amplifier or a passive high-pass filter. The only difference between this and a passive high-pass filter is that this system gives us a gain and increases the voltage. And the gain is determined by the active part, which in this case, because it's a non-inverting amplifier, it's going to be equal to 1 over R2, 1 plus R2 over R1. If this was an inverting amplifier, A would be negative R2 over R1. If it was a buffer, A would be simply 1. Or voltage follower, it would be 1. So an active high-pass filter is a combination of a passive high-pass filter, which is this part on the left, and an active element which determines the gain. The active element usually doesn't have any effect on the cutoff frequency. And the gain for an active high-pass filter is as follows. So voltage gain is going to be V out over Vn. It's going to be AF times F frequency over FC, which is the cutoff frequency, over square root of 1 plus F over FC in the power of 2. AF is the pass band gain, or in other words, the maximum gain that you see in the system, which is equal to 1 plus R2 or R1. This one is a non-inverting amplifier. F is the input frequency of the signal in hertz. FC is the cutoff frequency. And I'll explain later how we calculate FC. FC is the same as a low pass filter. It's going to be 1 over 2 pi RC. So just like low pass filter, the operation of a high pass active filter can be verified from the frequency gain equation. And if F or the input frequency is less than the cutoff frequency, in other words, if our input frequency is around here and our cutoff frequency is around, let's say here, F is less than FC, therefore V out over Vn would be less than AV. In other words, it's going to block this frequency. So this is going to be the stop band or the block band. If F is equal to FC at this point, F is equal to FC, then A, or the gain, or V out over Vn, would be 0.707 of the maximum gain, or AF. So this is 0.707, and this is our maximum gain, AF. And anything above that is going to be almost equal to AF. So if this is the frequency F greater than FC, then A would be equal to AF. Draw this a bit different. Here, F is less than FC. At that point is equal, and here we have it. Same thing that we had with the low pass filter. We usually calculate gain in dB, and AV gain in dB is going to be 20 log of V out over Vn. The cutoff frequency is going to be negative 3 dB, or 20 log of 0.707 V out over Vn. Since this is a first order active high pass filter, the drop of the gain at FC would be 20 dB per decade. For a second order, it's going to be 40, double this, for example. And at FC, the gain is 0.707 or square root of 2/2 of AF. And after all, FC, all frequencies are passband frequencies. So the filter has a constant gain of AF. In other words, it's going to pass the frequency. Now, how do we determine the cutoff frequency? We determine the cutoff frequency using this equation. Again, it's similar to what we had in low pass filter. FC is going to be equal to 1/2 pi RC. Okay. The other thing that we have in an active high pass filter is what we call a phase shift. Active high pass filters usually have a phase shift. And the phase shift is calculated using this equation. Phase shift would be equal to the tan inverse of 1/2 pi RC, or arctangent of 1/2 pi RC. This is it's equal to positive 45 degree at the cutoff frequency, FC value. And the reason that we have this phase shift is because of the passive RC filter. We know that for a non-inverting amplifier, we don't have any phase shift. For an inverting amplifier, we have a 180 degree phase shift. So this phase shift is the results of the passive filter or the RC filter. So another point is that in the previous circuit, we learned that we can build an active high pass filter using non-inverting amplifier. We can also build it using an inverting amplifier. And for this particular case, the cutoff frequency remains the same. It's going to be, again, 1/2 pi RC. R being this R1 connected to the C. And the only difference between these two is the gain. Gain here for an inverting amplifier is negative R2/R1. The frequency response curve for an active filter looks like this. If we didn't have any feedbacks, we're going to have this curve over here, which is an open loop without any feedback. When adding the feedback, we can control the gain and we can have a better frequency response. For an active high pass filter, FC, this is FC, the cutoff frequency. And in theory, if we just had a passive high pass filter, we wouldn't have any upper cutoff frequency. But since this has an active element, the op amp is going to limit our upper cutoff frequency, and we're going to have this crossover point, which is our upper cutoff frequency. And again, this F2 or FH is going to be equal to F unity or gain bandwidth over A. But for this particular case, we assume that the gain of the closed loop op amp is 40 dB. But obviously you can increase it or decrease. If we increase the frequency, the gain, you can see that the upper cutoff frequency would decrease each time that I increase the gain, you're gonna have a different result. So at this point, actually, it's gonna just directly come back. So you're not gonna have a very good frequency response. If you have 80 dB, for example, gain, your frequency response would look like this, which you would have a very, very limited frequency response. So the lower the gain is, you're gonna have a wider frequency response. The higher the gain, you're gonna have a narrower frequency response. Now, let's solve an example. I'll give you 5, let's say 7 minutes to solve this. It's an active high-pass filter, has a pass band gain of 2 and a cutoff corner frequency of 1 kilohertz. If the input capacitor has a value of 10 nanofarad, calculate the value of the cutoff frequency determining resistor and the gain resistors in the feedback network. Also, we want to plot the expected frequency response of the filter with a cutoff corner frequency given as 1 kilohertz and a capacitor of 10 nanofarad. The value of R, what would the value of R be? I'll give you a few minutes. Everyone completed? Yes. Usually get the same number. So R using the equation F is equal to 1 over 2 pi RC. If therefore R would be 1 over 2 pi FC. So it's going to be 1 over 2 pi frequency 1,000 kilohertz. And so 1 kilohertz, so 1,000 times 10 times 10 to the power of -9, because we have a 10 nanofarad capacitor. And therefore, the capacitor will be 15.92 kilo ohms, and the nearest that we can find in a lab is 16 kilohertz. So get back to, just give me 1 second. My computer just. So we already found R1, now we need to find R2. As the value of the resistor R2 divided by resistor R1 gives the value of 1, then the resistor R1 must be equal to resistor R2. Since the passband gain is 2, we can therefore select a suitable value for 2 resistors. For example, we can say it's a 10K for both feedback resistors, because again, gain is 2. So R2, R1 could be 1K, 1K, 2K, 2K, 10K, 10K, 100K, and 100K. They must be equal to 1. So for a high pass filter with a cutoff corner frequency of 1 kilohertz, the value of R and C will be 10K and 10 nanofarad. The value of the 2 feedback resistors to produce is going to be 10K both, or 100K both. And the voltage gain we already know is V out over Vn, which is F over Fc square root of 1 plus F over Fc on the power of 2. And the rate, the frequency ranges from 100 hertz to 100 kilohertz into the equation. If we just replace 100 hertz to 100 kilohertz, we can plot the frequency response, and it's going to look something like this. Starting from 100 hertz, the voltage gain would be 0.2, or in dB, it's going to be -14. 200 hertz, it's going to be 0.39. 500, it's going to be 0.89, so less than 1. So up to 800 hertz, you can see that it's actually decreasing and blocking the frequency. 800 hertz is going to be 1.25, 1,000 is going to be 1.41, 3,000 is going to be 1.91, 5,000 is going to be 1.96. So you can see it's getting pretty close to the 2, gain of 2, which is our maximum gain. And 0.7 of 2 is actually 1.41. So this is our cutoff frequency, which is 0.707 of the maximum gain, which is 2, gives us 1.41. So this frequency is going to be a cutoff frequency. Anything above this is going to be our stop band. Anything below this is going to be our pass. In the table, I mean, or the upper frequency. So if we draw the frequency response, it's going to look like this. So this is just for up to 100 hertz. Obviously, if you go down to 0 hertz, it's going to just continue and getting down to 0. This should be around maybe even 10 hertz or something like that. So the cutoff frequency, we can see that it's around 1 kilohertz. That you can see we have a 3 dB or 0.707 or the maximum gain AF. Anything after this cutoff frequency is going to be the pass band, and anything before this or lower than this is going to be our stop band. This is going to be our pass, and this is going to be our stop band. So anything after the 1K kilohertz, the gain remains constant at 6.02 dB, or the gain is 2. The upper frequency limit of the pass band is determined by the open loop bandwidth of the operational amplifier used, as we discussed earlier. And the plot looks like this. Now, some applications of, did you write it down? Did you write the solutions down? Do you want me to go to the previous slides? Okay, can I move on? Okay. Now, what are some applications of high-pass filters? Some applications of high-pass filters include audio amplifiers, equalizers, speakers, for reducing any low frequency or rumble type distortion. It's used also in radio communication systems, video, audio filtering, and in audio application, the active high-pass filter is sometimes called also the treble boost filter as well. Second order high-pass filter. So by adding another passive filter, another capacitor resistor to the system, we can create a second order high-pass filter. Why do we need a second order high-pass filter? So from this previous picture, we can see that this high-pass filter is not very accurate. It has a cutoff frequency, but the cutoff frequency, the cutoff or the stop band has a very pretty smooth angle, and it decreases 20 dB per decade, so it's not a lot of decrease. If we need a sharper cutoff frequency or something, or a sharper filter that looks like this and filters any unexpected frequencies, then we need a higher order frequency. So this is a second order high pass filter, or HPF we call it. And this is a first order. The first order HPF, or high pass filter. And a third order is going to look like this. 10th order. So higher the order is, you're going to have a sharper filter, a better filter. Okay. Not going to draw the second, third, and fourth because it's going to confuse you. An ideal high pass filter would actually look like this. You're going to have a cutoff frequency at the cutoff, and it's going to have like a square filter like this. This is an ideal. Obviously, we know we never have an ideal high pass filter. And when you have something that is very high order, you're going to have what we call it overshooting, meaning that changing from this, you're going to have a little bit of overshooting. You're going to probably learn this in signals and systems. But second order is commonly used. And the way that we build a second order is by simply adding another passive filter or an RC filter to the first order. Or we can cascade two first order filters and create a second order filter. For a second order high pass filter, active high pass filter, the gain AV is going to be 1 over R2 over R1 plus R2 over R1, which is the same as the first order for a non-inverting amplifier. But the cutoff frequency FC is going to be 1 over 2 pi square root of R3, R4, C1, and C2. So for the first order, FC was 1 over 2 pi RC. We had 1 R and 1 C, 1 C, but here we have 2 R's and 2 C's. So FC is going to be 1 over 2 pi over square root of R3, R4, C1, C2. High order high pass filters such as third, fourth, fifth, etc. are formed simply by cascading together first and second order filters. For example, a third order high pass filter is formed by cascading in series the first order and a second order filters. A fourth order is cascading 2 second order. Fifth order would be 2 second orders and a first order, something like that. Then an active high pass filter with an even order number will consist of only second order filters, while an odd order number will start with a first order filter and at the beginning as shown. So this is how we build higher order filters. It's the same for a low pass filter, active low pass filter, and high pass filter, passive and active high pass and low pass filter. For a first order, we just have one first order, second order, a second order. Third order would be a combination of a first order and a second order. Fourth order would be a combination of a second order with another second order. Fifth order would start with the first order and two second orders. Seventh order would be one first order and three second orders, for example, etc. Usually, I've never seen anything in practical more than like fifth order. It's gonna make a lot of build a lot of complexity unnecessary. It's got to make it very, very complex. Although there is no limit to the order of a filter that can be formed, as the order of the filter increases, so does its size. Also, its accuracy declines. That is the difference between the actual stop band response and the theoretical stop band response also increases. If the frequency determining resistors are all equal, R1, R2, or R3 are equal, and the frequency determining capacitors are all equal, C1, C2, C3 are equal, then the cutoff frequency for any order of filter would be exactly the same. However, we cannot, even if you open a box of same resistors from the same manufacturer built on the same day, you're going to see, and you saw that in the lab as well, that they're going to have different values. 1K has a 5% tolerance, so it's going to be between 1,000 and 1,950. You can't find two resistors that are exactly 1K from the same batch, from the same factory. However, the overall gain of a higher order filter is fixed because all the frequency determining components are equal. Again, because of in real world, we're not going to have that. You're going to have a small difference between them. In the next slide about filters, we will see that active bandpass filters can be constructed by cascading together a high-pass filter and a low-pass filter. So an active high-pass bandpass filter, again, as I mentioned this before as well, it's a combination of a high-pass filter and a low-pass filter. If we want to have a passive bandpass filter, we don't need the amplification. We just connect a high-pass filter with a low-pass filter and we create a passive bandpass filter. If you throw an amplification in the middle, that could be a transistor, it could be an op-amp, any type of amplification or active element, then we create an active bandpass filter. So an active bandpass filter is a combination of two filters, which is a high-pass and a low-pass filter, and an amplifier in the middle. The principal characteristics of a bandpass filter, or any filter for that matter, is the ability to pass frequencies relatively unattenuated over a specific band or spread of frequencies called the pass band. So a bandpass filter, as mentioned before, looks like this. It has a lower cutoff frequency, upper cutoff frequency, this is called FL or F1. This is called FH or F2. Anything in the middle is called a pass band. And anything lower than the lower cutoff frequency and higher than the upper cutoff frequency is called the stop band. Stop band and stop. So this is a schematic of a active bandpass filter. On the left, we see the passive high pass filter, HPF. And on the right, you can see the low pass filter. And in the middle, you see the active element, which is the amplifier. already mentioned here, amplification. So cascading together two individual filters, high pass filter and a low pass filter, produces a low Q factor. We already mentioned, I think, in electronics, if you were with me, the Q factor is the operating point. Produce a low Q factor type filter circuit, which has a wide pass band. The first stage of the filter will be the high pass stage that uses the capacitor to block any DC biasing from the source. This design has the advantage of producing a relatively flat, asymmetrical pass band frequency response, with one half representing the low pass response and the other half representing the high pass response, and the middle would be the active element. And the graph, actually, the response looks like this. You have the high pass half and you have the low pass half, and when you combine them together, you're going to have a band pass. And the upper, or the FH and FL, is calculated using the same equation that we had. F is equal to 1/2 pi RC. I'm going to solve more practice problems for this. I think we are out of time. 10:20. Yes. Yes, please. Thank you so much.
On your band pass on the right,
Yes.
that max amplitude there, is that your band pass area?
Yes, that's a bandpass gain determined by the active filter. That's a great question, by the way. This is the, here you can see the maximum gain, or we call it AF. Yes, and this is determined, this is actually the gain of the op amp, which in this particular case, it's in non-inverting, so it's going to be 1 plus R2/R. Thank you so much, and I'll see you on Thursday.